I assume most of you have at this point. I'm Caitlin. I work with Eli at the Cloquet Forestry Center as the Education Program Specialist for SFEC. You will be seeing me all throughout next year on our webinars as well, because I'll be leading our 2021 webinar series. I can't believe that it is already December. This is our last webinar of this year. So thank you so much for joining us. And I just wanted to let you all know to watch your inboxes. We're going to send an announcement next week promoting and advertising registration for our 2021 series. So we hope that you will join us again for some of those. We have a great lineup of speakers already in place, and we're really excited to announce that. So again, registration will be opening for that soon. And a couple other things about it that we'll include in the email. Based on some feedback from our audience, we're actually going to try something new with the timing of our webinars. So we're still going for the second or third Tuesday of every month, but instead of at noon, we're going to change them to 9 a.m. So webinars will be from 9 to 10 a.m. next year, shake things up and see how that goes. And we're also going to be changing the cost structure. So instead of being able to purchase the entire series or pay for individual webinars, there's just going to be one set price. So for members, you can purchase the entire series for $35, and for non-members, $35, and for members, you can purchase the entire series for $20. So once you've registered for one webinar, you'll just have access to the entire series. So that should make registration a little bit easier. And with that, I'm going to kick it over to Matt to introduce our speaker today. So again, watch for that email, and thanks for joining us today. All yours, Matt.
Great. Thank you, Caitlin. Before I introduce Grant, I wonder if you want to go ahead and share your screen to go ahead and get us started. I do want to mention, if you have questions, to put them into the chat area. We might have a time for questions to kind of pause sometime during Grant's presentation if he wants to take a quick break to answer some of those questions. Otherwise, we'll have questions and time at the end to do that. So if you send those questions in, again, send them to definitely send them to all panelists, or if you want others to see the questions, send to all panelists and all attendees. So either way, we want to make sure that we get your questions so that we can relay those to Grant. So do go ahead and do that. With that, happy to introduce Grant Domke. So Grant is a part of the Northern Research Station with the U.S. Forest Service based in St. Paul. Many of you that are on the call today want to learn a little bit more about forest carbon. I like to call forest carbon possibly the currency of the 2020s when it comes to our forests, maybe one of our most valuable forest products. And so Grant will talk about what he does and his role in looking at forest carbon and how it relates to greenhouse gas emissions and removals from forest land in the US. And so really happy to have Grant a part of this webinar series today. So again, if you have questions, type them into the chat and we'll pause and at a convenient time, kind of in the middle, and then maybe again at the end to relay those questions to Grant. And so with that, Grant, feel free to take it away.
Great, thanks, Matt. Can you see my full screen? Is it all right?
Yep, looks great.
Okay, thanks a lot. Well, thanks very much for the opportunity to share a little bit about the work that we do as part of the Carbon Science Group in the Northern Research Station FIA program, Forest Inventory and Analysis Program. So as Matt said, I work with the Forest Service in St. Paul, Minnesota. And while I sit in Minnesota, our responsibilities, or the group's responsibilities, is really national and international in scope. And so we don't take a deep dive on the state of Minnesota or even the region that we work in necessarily. Although I hope throughout this talk that you'll see that we're really trying to take a deep dive really everywhere in the United States through integration and harmonization of a variety of different data sources. Sort of the foundation of which is the National Forest Inventory, the FIA program, the data that's collected as part of that program. I'll go ahead and start here. A lot of what I'll be talking about today is really a group effort. It's very much a collaborative effort. We're a pretty small team within the Northern Research Station. And so we really rely on partnerships and collaborations to get the work that we do done each year. And that work is in part national, state, and entity level greenhouse gas reporting within the forest land category and the land sector more broadly. But also the lion's share of the work that we do is really research in support of those reporting responsibilities to improve the methods, models, and data that we use to characterize forest carbon and more broadly greenhouse gases on the land in the United States. So I'm going to go ahead and begin with the end. I'm going to give away the punchline of the talk in my very first set of slides here. And I'd really like to set the context for the work that we're doing, the scale at which we work, and sort of the complexities of tracking carbon within forest land, but really more broadly across the land sector in the United States and really globally. So this cartoon is obviously a very simplistic characterization of the land sector and how the land sector and particular land use categories. We recognize 6 different land use categories as part of the work we do to compile estimates to the United Nations Framework Convention on Climate Change. The forest land category happens to be the largest in terms of the removals in the United States, but you can see here that there's a lot of interaction between the land use categories and also within each category. There's transfers of carbon within the forest land category that we'll get into a bit in this talk. As trees die, that carbon is transferred, some back to the atmosphere, maybe through combustion due to a wildfire or decomposition from microbial activities. But also some of that is transferred into deadwood. And so we're tracking the status of that carbon as it moves through the ecosystem, but also as it moves between ecosystems and land uses, as well as harvested wood products, and then back to the atmosphere. So all of this collectively, we sort of treat as a transfer in one direction or another, whether it's back to the atmosphere, from the atmosphere, to a land use category, or between those categories. So here I've highlighted all of the different components that our carbon science group within Forest Service contributes to as part of our international responsibilities with the United Nations Framework Convention on Climate Change. So each year we're compiling estimates of the greenhouse gas emissions and removals associated with all of these components and the interactions of these components each year. And collectively, all of these components sort of in total represent a net removal from the atmosphere of approximately 752 million metric tons of CO2 equivalent. And I know that's a big number, and we'll put that into some context here in just a little bit. But in a nutshell, that's the equivalent of 11% of the economy-wide greenhouse gas emissions in the United States emitted each year, about 1.3% of global emissions, and about 14% of carbon dioxide emissions. So the forest land category represents about 95% of the sink strength in the land sector. And so it gets a lot of attention. And we see forest land and forest management as being one cost-effective way to sort of mitigate the effects of emissions through sequestration and positive interactions with the atmosphere. So why is this important? So I'm sure many of you are familiar with these curves. This is really a modeled record from ice cores, and then more recently, the Keeling Observatory, the observatory on Mauna Loa, tracking CO2 concentrations in our atmosphere, as well as historic emissions. And you can see that historic fossil fuel emissions, as well as, frankly, a representative concentration pathway of 8.5, which when these pathways were originally established, this was considered an aggressive pathway and sort of an extreme case. And unfortunately, a recent look at this pathway in relation to actual concentrations of CO2 in our atmosphere suggests that in fact it is characterizing the increases in CO2 quite closely. I guess what this is really telling us is that there is this coupling or this correlation between fossil fuel emissions and increased concentrations of CO2 in our atmosphere. And why is that important? Well, we know that CO2 and other greenhouse gases have a deleterious effect, act as sort of a blanket, if you will, and cause warming to our atmosphere and to the Earth's surface. And this warming and other environmental changes as a result of these increases in concentrations of not just CO2, but other greenhouse gases in the atmosphere were really acknowledged back in the 1960s as having sort of deleterious effects or impacts on humans and the natural environment more broadly. But it wasn't really until the late 1980s and early 1990s that the United Nations really stepped up and said, hey, we need to act in the interest of human safety, even in the face of scientific uncertainty. And that was really the dawn, if you will, of the United Nations Framework Convention on Climate Change. It was entered into force in 1994. The United States was a signatory to the convention from the very beginning. And the US is considered an Annex I country. And so what that means is we're required to report on economy-wide emissions each year from the years 1990 to 2 years before present. And when I say economy-wide emissions, really that means any emissions associated with the US economy, including the land sector, where we've got sort of agriculture and forestry and the other land uses that contribute in some way to the US GDP and the economy more broadly. And so the idea behind this convention was really to stabilize greenhouse gas concentrations at a level that would prevent dangerous anthropogenic interference with the climate system. And so since this early convention was established, you're probably all very familiar with the fact that there have been a number of proclamations and accords and agreements established, the Kyoto Protocol, and more recently, the Paris Climate Agreement in 2015 and 2016, to sort of curb or bend the curve, which is, I think, something all too familiar that we're hearing a lot related to the global pandemic right now, of these CO2 emissions in our atmosphere, and how can we as humans slow the increase in this CO2 and hopefully stop those increases through international treaties and cooperation. So that's where our team comes in. So the team was really established right around the time that the United States signed on to the United Nations Framework Convention. And it's the mission of our group has sort of evolved over time from just reporting as part of this, this international agreement to advance the science, monitoring, and reporting of greenhouse gas emissions and removals on not just forest land, but really we've grown this responsibility to land with trees in the United States. So this talk will include estimates for urban trees and settlements, as well as woodland trees outside of the forest land category, what we typically consider forest land from an FIA definition. And increasingly, this work is really to help land managers and policymakers evaluate existing practices and policies and to inform future activities. So while a lot of the work we do is really to compile estimates at this really large national scale, we're working really hard and have made a lot of investments over the last number of years, as well as a lot of proposals and projects currently underway to distill this information and disaggregate the information to a scale at which land managers and policymakers can use that to inform, decisions that are really happening at the stand and landscape, not at this national scale. So this is sort of a national snapshot of the contributions that our group makes to the land sector greenhouse gas emissions and removals in the US each year, and really summarizes that number that I described earlier over this entire time series that we report on, 1990 to 2 years before present. And so you can see that the major, so negative values here represent a removal from the atmosphere. So that's a good thing. That represents a sequestration or net removal from the atmosphere, whereas positive values throughout this talk represent an emission or a transfer of carbon to another land category. And so you can see here that the sink strength has remained relatively stable over the time series, with some interannual variability, and that interannual variability can be attributed to, in large part, wildfire, particularly wildfire in Alaska, but also in the Western United States more broadly, and to a lesser extent, land use change. So land use changes over the time series. So you can see the major contributor to the sink strength in the United States for the categories that our group compiles are, not surprisingly, those forests that have remained in the forest land category over the time series. So these are forests that are growing and sequestering carbon in live trees, and that carbon, as those trees die, is accumulating in dead organic matter and in soil. And so the sink strength really is driven in large part by this this positive interaction with the atmosphere from live trees and a relatively stable forest land base in the US. The other major contributors here are land conversions into the forest land category. And this includes both afforestation, but also reforestation, where land had been cleared, maybe following European settlement, and has slowly or rapidly sort of evolved back or succeeded back into what we define as forest. The major sources of carbon loss within the land sector, and particularly the forest land category, broadly speaking, are really emissions associated with land conversion. And so this is the case in pretty much every state, but most of the land conversion we're seeing that's at least driven by human activity is in the eastern United States, and much lesser extent in the West. Most of the conversion we're seeing in the West is driven by natural disturbance. So an important category and contributor to overall emissions and removals each year. So just to sort of boil this down into terms or units that might be more familiar, over the entirety of the US land base, and there's right around 280 million hectares of managed, what we define as managed forest land in the United States. This sort of sink that we've described, or I've just described, translates into a net removal from the atmosphere of about 2.1 metric tons of CO2 equivalent per hectare per year. So across all of the forested land base in the US, it is a net sink. But as you'll see in a minute, that sink isn't distributed uniformly across the US, and there are certainly hotspots for emissions, as well as hotspots that are serving and have historically been net sinks. So to provide a little more context, that 2.1 metric tons of CO2 equivalent is the equivalent of about 5,000 miles driven by the average passenger vehicle each year. And the total sink strength that we described, that 752 million metric tons of CO2 equivalent, represents more vehicles, passenger vehicles, than are actually on the road in the United States right now. 163 million passenger vehicles, or the equivalent of about 194 coal-fired power plants in 1 year. So a really substantial contributor to the overall carbon budget in the United States. And there's room, we believe, based on recent research and a lot of statistics and data, to increase the contribution of forest land in the land sector as a nature-based solution to mitigating climate change. And we'll get into that towards the end of the presentation. So before we do that, how are we compiling these estimates of greenhouse gas emissions and removals in the US? Well, as I mentioned, I work in the Forest Inventory and Analysis Program, and it's really those data from the National Forest Inventory that serve as the basis and foundation for these estimates of carbon stocks and stock changes in the forest land category, but also associated with land conversions. And so the US inventory, for those that are not familiar, was really established back in the late 1920s. And Minnesota was really sort of a staple in terms of the U.S. National Forest Inventory. Inventories began in the 1930s in the Great Lakes region and the Lake States in particular, and has really continued did continue as a timber inventory through the late 1980s and into the 1990s. And then with the passage of the 1998 Farm Bill, the inventory was expanded substantially in terms of both funding, but also the scale at which we were collecting information. And it really transitioned from a timber inventory on productive forest land to a comprehensive inventory of all ecosystem attributes across all ownerships and land in the United States, with an emphasis on forests. And so now we consider this sort of a comprehensive survey of status and trends in the forest land category. And the definition of forest land is rather long. I'm not going to go into it here. I've included it just so you have this. I know this is being recorded, but really we can boil this forest land definition down to 4 key attributes. So the footprint must be 1 acre in size. It must be at least 10% canopy cover. Trees must be able to obtain a height of 5 meters. So the site must be productive enough to support tree growth and tree heights of 5 meters. And finally, it must be classified as a forest land use. So orchards and other agricultural, situations are not included within the forest inventory. And so there are some cases where 3 of the 4 criteria are met, but if it's not classified as a forest land use, then we are not actively sending field crews out to measure those plots that fall on those land uses. So just a little bit in terms of the distribution of the FIA plots in space. So we tessellate the globe with these hexagons, and conveniently these hexagons nicely nest within one another at finer and finer spatial scales. And the way these hexagons are tessellated, there's one hexagon over the entirety of the continental United States. And that hexagon then is made up of a series of smaller hexagons. And these smaller hexagons are then overlaid on a forest, non-forest layer, which you can see here over the state of Minnesota. And you can see it's part of a pre-field process. The first thing we do is identify forest land from non-forest land, overlay those core field plots, which each plot or each hexagon represents approximately 2,428 hectares. And then there are a series of more intensive plots collected over a subset of those core plots. So every 8th plot or every 16th plot, we're collecting additional information on site and tree specific attributes, which I'll describe a little bit right here. So here's an example of one panel of hexagons where you can see the individual colors represent a unique year within a panel. So this panel represents sort of the 5-year remeasurement period, like is done and has historically been done in the state of Minnesota. So each year, one of these panels would be a plot within one of these panels would be evaluated. And so it's spatially representative, it's equal probability. And so you only need 1 year's worth of data to actually make an unbiased estimate, or to obtain an unbiased estimate of a land area and volume and carbon and other attributes. And as you gain plots throughout the panel process, you basically your precision should improve. You should see the uncertainties get smaller and smaller. So, but your estimate should be relatively similar between those individual panels. So The nice thing is you can use sort of a rolling average, and increasingly we're looking at alternative estimators to use individual year data. So individual panels of data rather than the 5 panels or an entire inventory cycle to make estimates to eliminate or reduce some of the latency that we see in terms of the remeasurements between these panels. You can also see here that as we scale in even further beyond the sampling frame that we use in the FIA program to the plot design, the plot is made up of 4 subplots. Within each subplot, there are a series of smaller plots and transects depending upon the scale at which we're measuring. Again, the core plots, we're really focused on tree and site level attributes. And then on those intensive field plots, we're collecting additional information on down dead wood, litter, soils, invasive species, individual plant species, etc. So here's the distribution of those individual field plots. They're permanent plots across all ownerships, like I said. And these are all the plots with at least one forest land condition in the lower 48 states. So there are roughly 130,000 of those plots that are sent to the field, and field crews measure every 5 to 10 years, depending upon where you're located in the United States. It's important to note for this talk, though, that there is really a broader suite of plots that we collect. And we're collecting information, not necessarily in the field, but using remotely sensed information. So high resolution imagery to assess and classify the land use on all non-forest plots. And it's that information that really helps us identify, classify land conversions as part of the inventory process, but also do a variety of other things in terms of classifying the land, estimating land areas, and the contribution of forests relative to these other land use classes in the US. So now that I've given you a little more context on how we're compiling these estimates using the National Forest Inventory, we're going to take a bit deeper dive on specifics, and we'll zoom in a little bit to the individual state level. And so here are 49 of the 50 states, or excuse me, 48 of the 50 states represented. All of the lower 48 states are in this graphic. Again, the negative estimates reflect a net removal from the atmosphere, and the different colors here represent the different forest ecosystem carbon pools and the contribution to those net emissions and removals for the year 2018. So you can see that there are many states that are really strong sinks, and there's a pretty substantial interaction with the atmosphere. Not surprisingly, most of those states are in the eastern US and in the southern part of the eastern US, where productivity is really high, management can be quite intense in some cases. And the inverse of that is the sources or emissions are largely focused in the western United States and really the Rocky Mountain region, where forests have been experiencing changes in the frequency and severity of natural disturbances, and particularly wildfire, over the last few decades, which has really evolved the sort of emissions and removals time series in those states as these natural disturbances have sort of changed in terms of the scale and also the severity over the time series. This is just another way to portray that information. So again, in this case, any states in yellow represent a net loss or an emission back to the atmosphere in terms of the totality of the forest land carbon sink, whereas the different shades of blue-green represent net sinks. And so you can see that, not surprisingly, the Pacific Northwest and the forests in that region are strong net sinks, whereas the majority of the Intermountain West represent a source or a modest sink based on growth rates in the Intermountain West. So all of this information that I've just described is available each year as part of our commitment to the United Nations as part of the US Greenhouse Gas Inventory Report. That information is summarized at the state level and at the national scale. For the most part, at the national scale, some things are state level statistics, But we also, our team has been compiling these estimates as part of a independent sort of resource update that's published on or around the same time that those official greenhouse gas estimates are released. And we summarize the national statistics in a 3 or 4 page document. But new this year is this appendix that we've included, this online appendix, which includes state level tables. It's all hyperlinked, so you can quickly jump to whatever state of interest. And all of the tables are organized and I guess developed and portrayed in the very same way that we portray the information at a national scale in the US greenhouse gas inventory report. And so if there's anything from the greenhouse gas inventory that you're interested in at a state level, this report documents it in one place in this appendix file. And so we're going to jump to the state of Minnesota just to give you an example. I'm not going to walk through the time series here, but just to illustrate, the level of detail that's available in this report. And this was for the first time released in April of this year. And we have plans to do the same thing moving forward, as well as providing this information through a series of dashboards and other platforms for those interested in this type of information. So you can see here for the remaining forest land pool in Minnesota, a pretty strong sink. And if you were to include the land conversions to the forest land category, the sink strength is around 15 million metric tons of CO2 equivalent each year. So a pretty strong sink in the state of Minnesota, which I guess is a really good thing. You can also see that we're collecting a lot of information related to non-CO2 emissions from things like draining of organic soils. In this case, the pluses represent an estimate that's less than 0.5 million metric tons of CO2 equivalent. We do have those estimates. We calculate them for everything. But again, we follow the convention used by the United Nations and established through the IPCC good practice guidelines, and just report them as pluses here. I'll draw your attention specifically to the fire emissions. You can see here the fire emissions are relatively modest for non-CO2. The CO2 emissions from fire are actually baked in. They're inherent within our emissions and removals estimates for the forest land category. But the non-CO2 emissions are calculated separately here. And you can see that it was really over the time series, just that Pagami Creek fire in 2011 that led to an estimate that was greater than that minimum threshold to actually report the estimate. And then just one final table here, looking at land conversions from other land uses into the forest land category over the time series. And again, a pretty substantial component here if you think about this in broad terms, a nice net sink here, which you would expect in these land conversions. There's also a source of information as a source of carbon released from the forest land category or transferred to other categories. And that information is actually collected and compiled as part of the other land use information, although we do distill that information down in these individual reports that I just described. So just to sort of close on this state level reporting information, you can see that this is table 225. I think in total there are more than 500 tables. And again, a lot of this very same information will be available through a sort of online dashboard that will allow you to quickly search out specific information for the different states in the US, including Alaska. And we're currently working on the state of Hawaii, where we're still using a periodic inventory where we're not measuring every 5 to 10 years. And so the information there from the NFI is not quite as rich as the other states, allowing us to build out the time series like we do for the other 49 states. So a lot of this information can be found as part of the Forest Inventory and Analysis's national webpage. We've got a specific page on forest carbon science and reporting, all the way from international reports that we contribute to through IPCC and UNFCCC, but also state level reports like I just described, specific 5-year and annual reports where we've included carbon estimates from the work that we do. as well as research activities that we're working on and data products that are available for the public to use or stakeholders, more broadly to use. All of that is sort of summarized here and provides contact information. If there's something that you're interested in but you don't see here, you can reach out to the group and we can let you know if we're doing things, or at least if we know of information that might be available for your needs. So now I'm going to jump into a little bit of some research activities inspired recently by some commitments the US has made in terms of how we might grow that sink strength in the US. So some opportunities to increase carbon uptake in our existing productive forests in the US, and also highlight a few challenges before closing with some of the research activities currently ongoing that I think will have implications or might be of use to the folks listening today on the webinar. So first of all, what this map portrays is really the area of poorly stocked and non-stocked, what we collectively sort of describe as understocked timberland. So the productive forest land in the US by state and also by ownership. And so the more close you get to red, the more area that's currently available, productive forest land area that's available. And not surprisingly, again, the states with the majority of forest land available for reforestation are those states that have been affected the most by natural disturbance in recent years, but also those where harvesting is quite common. So here you can see that particularly the northern part of the Western US, there represents a really great opportunity to restore and to reforest existing forest land. That's an important piece here. So this analysis, we really focused on existing forest land where there's been evidence of trees growing and productivity meets a minimum threshold within the database and within the classification schema used by FIA. We can also see that the opportunities sort of change nationally as you move from east to west in terms of ownership patterns. And so this served as sort of the basis for us to evaluate. So, if we were to start making investments in reforestation activities in the US, say as part of our commitment to the Trillion Trees Initiative, first of all, we want to make sure that we're not just blindly planting trees anywhere, but we need to target those investments in areas where it makes sense. And so we use the FIA data to assess, again, just this existing forest land and productive forest land, where are existing carbon stocks? So where is the live tree carbon density? And what we found was that in most cases, the majority of the standing carbon per unit area, highest per unit area estimates are on federal forest lands, followed by private lands, and then state lands are close behind. But really, there's the distribution of carbon across the stocking levels is pretty consistent across the three ownership categories. Interestingly, though, when you start to look at annual changes, so the removals on these forest lands, it's clear, sort of this clear signal on which lands are more productive than others. And it's really the private forest land that starts to jump out in terms of being more productive. And I think there's a lot of land use and historic agreements and the way in which land tenure is established and land ownership is established that sort of point to these patterns that we're seeing here in terms of per unit area estimates of standing stock, but also removals associated with those for existing forest land in the US. And so based on all this information and the understocked forest land in the US, what we found was that if you were to fully stock these areas, targeting these areas that we have evidence of historic productive forests, we could increase the sink strength in the US by roughly 20%. And so that's a substantial increase in terms of the overall contribution of existing forest land. But we also recognize, and so to do that, you really need to concentrate or target these investments. And what we found was that, finding these highly productive areas that are currently poorly stocked and doing that on the most productive sites, which is, in this case, predominantly private land, but also to a lesser extent, federal and state lands, you can really make a big impact, but concentrating these plantings is really important. What we also found was that there are really challenges in this. So it's not just about, going out there and carte blanche saying, well, we know this is productive forest land, and we know what the full stocking level is, and what is the sequestration potential if we fully stock these areas, because we know that natural disturbances, as well as just changes in our climate, extreme drought and other things, have made conditions less favorable in certain environments. And also, by fully stocking some of these areas, particularly in the Western US, you might just be inviting wildfire, which leads to greater emissions. And so, first of all, it's not just about carbon. We need to really be thinking about the multitude of benefits that trees and forests more broadly provide, but also, look specifically, really make place-based decisions based on current and historic disturbance dynamics, the trees that exist now and those that we believe will be resilient and resistant to future changes to the climate and disturbances. And so this is some work that's sort of built on some earlier work looking at sort of reforestation potential in the US by looking at, what are some of those challenges. And this specifically, we targeted the 8 most abundant tree species in the Western US. And unfortunately, it appears that 5 of the 8 species, particularly the montane species and subalpine species, are declining rapidly over the last 20 years in terms of their overall abundance and also by size class. And those declines are driven to a large extent due to fire and insects, and to a less extent disease. And so, I think this again provides some clues to managers out there in terms of, how we manage and what the forests of the future might look like to make these stands more resilient, so that we can at least maintain forest and the multitude of benefits that forests provide in the face of the this changing environment and changing disturbance dynamics, particularly in the Western US. The East is certainly not free from disturbances, and what we once described as novel disturbances in terms of wildfire and expansive wildfire in parts of the Appalachian region are not so novel anymore. And we're seeing more and more fires each year in some of these areas, which I think exacerbate the sort of or exacerbated by by changes in climate and other natural activities. So I guess a lot of this research has led us down this road of realizing that the strategic level inventory is really important, and that it can serve as a foundation for things like national level reporting. But as we start to zoom in, and attribution of these fluxes becomes more and more important. So what are the drivers of these changes in forest dynamics? We need to start integrating these inventory data with auxiliary information, so largely remotely sensed information, to make finer and finer spatial characterizations of the land in each year, so that we can identify what are the drivers of change and how can that information be used to inform land management and policies to sort of avoid these emissions, or take steps to make these forests more resistant and more resilient to sort of the natural stressors or pressures on them, but also to help land managers better understand the contribution of their forests to this national picture. So how can we scale, the forests at say a 30 meter or 1 hectare scale up to the nation, so that we can start to identify these hot spots in areas of really strong sinks, but also of sources, and learn from those areas and how those forests might be unique, and what can those forests tell us about how we think about management and manipulating or altering policies in the future to leverage the benefits that forests provide in terms of climate mitigation. And then finally, to sort of support some of this, our team will be taking over the consistent representation of land as part of the US greenhouse gas inventory in 2022. And so this is a characterization of managed and unmanaged forest land in the CONUS and Alaska. And so we will actually be moving beyond the forest land base and characterizing the entire land in the United States with spatially explicit and spatially continuous data products over the entire time series moving forward, leveraging a lot of assets from Forest Service, but also a lot of remote sensing data, NRI data from the Natural Resources Conservation Service. So I think it will be one of the largest aggregations or integrations of national forest inventory data with Natural Resources Conservation Service data, NLCD information, as well as a lot of independent points and CFI data to build out a sort of foundation or baseline of the land and how that land is changing over time. And this will serve as sort of the basis for developing products like I just showed at really high resolution that can be scaled to the nation for greenhouse gas reporting to the UN, but also be used by states and entities for their reporting purposes and research. So a few final thoughts. Forest Service continues to expand our role in greenhouse gas science estimation and reporting, as I just noted. And this is really just, I think, a brief summary of the research activities that are currently underway to sort of build out and facilitate this kind of information and provide this information to the stakeholders interested in it. FIA data, though, continues to be the foundation, even though we've got loads and loads terabytes of remotely sensed information. The FIA data really continues to serve as the basis for which we're compiling everything from the entity all the way to the national, international scale. All of this is, the motivation for us from a sort of research perspective is to develop more spatially and temporally resolved information to facilitate attribution of these fluxes over time, which we hope then will inform land management and policy. And we can't do this alone. So like I opened the talk, we're a small group. And so a lot of the work that we do with Matt Russell's group, he's probably our closest collaborator. He's got a big team of people working with Forest Service to help us improve the work that we're doing in this space. And so we're always looking for new partners and collaborations to build this work out and provide information that's useful to folks at a variety of spatial and temporal scales. So with that, I think we've got about 10 or 15 minutes left. We can get to some questions.
Yeah, there have been some great questions coming in. Thanks for your presentation, Grant. That's a great overview of your role in greenhouse gas reporting and how all the plot measurements, people wrapping diameter tapes around trees, how that turns into, what we know about greenhouse gases and the role that forests play. I'm going to just kind of go through these as they have come in. I've got about, I guess, 8 questions in front of me, Grant, just kind of as a time check, thinking that we'll try to wrap here by 1 o'clock. But again, if you have questions, type them into the chat area and we will relay those to Grant. One that came in, Grant, is related to grasslands. Can you kind of compare grassland, how much they sequester relative to forests? Any ideas kind of top of mind come to you?
Yeah, I can. So we actually compile the woody biomass component of grasslands. So our group is not charged with that as part of our international reporting responsibilities, but the woodland component alone is around 15 million metric tons of CO2 equivalent a year. And so that's sort of a new element for the grassland category, which is compiled by Stephen Ogle and his team at Colorado State University. That's based again on FIA data, where we recognize that there are FIA plots, particularly in the southwestern United States, that don't meet the definition of forest land, but are where there are land with trees. But the other big piece is really the soil. So a lot of the grasslands, those annual grasses, there's an assumption that those grasses they grow and they die, and so the net I guess mass balance is a net zero, and so it's really just the soil carbon and the accumulation or loss of soil carbon in those grasslands that's compiled. And so, like I said, forest land account for about 95% of the sink strength in the land sector. Grasslands maybe 1% overall, so a pretty small component. But I'll also add that we have a lot of research underway right now to characterize all those land with trees out there that Forest Service hasn't been, measuring, which don't meet our definition of forest land, but we, for some reason have that information on FIA plots. So we're using remote sensing to capture that carbon in those other pools in areas like the Great Plains that, there are windrows and other areas, millions of hectares out there of trees that aren't currently captured in the national inventory. So stay tuned. I think those numbers will change. And I think the contribution of grasslands will certainly be a much larger part of the inventory in the years ahead.
Yeah, on that same topic, someone mentioned learning from someone that said if a prairie is burned, root growth increases and results in a net increase in carbon retention. This person even guessed that the same amount would happen when a forest burns. Do you have any comments on that?
Sure. So full disclosure, I'm not a grassland ecologist, but I do know that grasslands, about 2/3 of their biomass is stored below ground. A lot of those below ground components are perennial, and so they don't die. Those rhizomatous mat structures can persist for long periods of time, and so a lot of the biomass, we see it in terms of land conversions. There's a lot of below ground biomass. When the above ground biomass dies, it can really expand and bolster the below ground components to sort of persist. And so, that aligns, that comment aligns with my understanding. Forests are quite a bit different, I think. There are a few exceptions for those species like the populous species where you manipulate the sort of hormonal imbalance or the hormonal balance of above and below ground structures. If you were to cut an aspen stand, for example, we know that below ground structures oftentimes persist. And it's really those structures that lead to, root suckering and regeneration and expansion in many cases of those coarse roots, and expansion overall of the below ground component. Trees, however, are the exact opposite of grasses, and about 1/3 of their carbon is stored below ground. And so I don't think the same is the case in forest land that you might see in grasslands.
Great, thanks, Grant. Going back to thinking about wildfire, your thoughts and what are about CO2 emissions from wildfire? Your thoughts on that and kind of what Forest Service might be working on there.
Yeah. Well, what I try not to share anything that hasn't been published or isn't in press, but of course you can imagine that we've received a lot of questions related to the 2020 fire season and the emissions, just given the magnitude in terms of area and severity of fires, particularly in places like California and the southwestern US more broadly. And yeah, fire has, well, you saw it. Even in recent years, I think there's a combination of factors in the Western United States that have led to the sort of losses or emissions. Number one, the forests in these regions grow differently and more slowly. The stocking in these areas is much different than what we might be used to, say, in Minnesota. These are open grown. As they mature, for example, lodgepole pine, as those forests mature, they start to fill up. And you can see this in the albedo signal of these forests. As they get older, they really start to get very dense until they burn up. And so, just the development of these forests is different. The process, it takes longer. Growth is slower, and recovery, unfortunately, is slower. And in cases where we're seeing repeat disturbances, increases in the frequency and severity of disturbance, particularly wildfire, but obviously there are complexes out there where you've got extreme drought that leads to longer instars or maybe additional instars of insects that lead to, the additional generations each year, which means even native insects are having a greater impact over larger areas in the West, and then wildfire on top of it. I think collectively, those complexes have led to, really catastrophic fires. And I've come to the realization that the way in which we manage these Western forests, in some cases, it's more about emissions avoidance rather than increasing carbon sequestration capacity. And so how do we manage and manipulate these systems to maintain them as forests and all the benefits that they provide, rather than, in a lot of cases, these Western forests prone to fire and other catastrophic disturbances. We shouldn't be targeting those as the carbon pump in the United States, and I don't think we are. There are other areas where we can target investments if carbon sequestration is the goal. In these cases, I think we really need to look to things like emissions avoidance, and what are some land management practices where we can maintain forest as forest and give those forests a fighting chance in the face of these changing sort of disturbance regimes.
Great. A couple other themed questions. I'm going to kind of group them to see because we're running a little bit short on time. One's on kind of looking at age as a predictor of carbon sequestration storage, and then one on kind of management. So the one on age, I mean, maybe just your broad comment about, there's kind of trade-offs between, how much sequestration happens at a young age versus an old age. And so one person asked about specifically 25-year-old aspen, does that sequester more carbon than more mature stands? So your thoughts on age and how it plays a role in thinking about carbon sequestration.
Yeah, I think it's a good question. So I guess my first piece would be that even an aspen stand, so an aspen stand in northern Minnesota is a very different tree, even though they're genetically identical, than an aspen stand in Colorado. That Colorado stand might be 200 years old, and the height might be 40, 50 feet taller than an aspen stand in northern Minnesota. They just grow very differently. It's a very plastic species, and I think that is sort of telling in terms of the species you're thinking about. So for example, there have been a number of studies recently and even over the last 25 years looking at thinning what we might describe as old growth pine, particularly red and white pine that are 200 to 300 years old. And thinning those stands and actually seeing a positive response. Occasionally there's a sort of a thinning shock, but there is a delayed response and increases in terms of the radial growth of these trees and sequestration. And so for those long-lived species, I think there are some benefits in terms of leaving those on the landscape, particularly if they respond to management, where they're continuing to sequester at high rates relative to other species, maybe like aspen, where there is a point where you start to reach that pathological rotation, particularly in a state like Minnesota when it's 40, 50, 60 years old, and you might actually have more decay, decomposition occurring, whether you see it or not, than new carbohydrate being put on from the interaction with the atmosphere. And so I think it's really species and site specific and geographically specific, but age is an important metric. And if you plot this, regardless what the species, typically you'll see increases in carbon stock with age, but that there's a point where that curve starts to flatten. And it's the same thing that we learned in forest biometrics and measurements in terms of maximizing mean annual increment. If that's your goal, if sequestration is your goal, there are ways in which you should be managing those individual species. But again, I would just stress that it's, we're thinking more about, or at least personally recognize that there's a multitude of benefits and there are trade-offs in terms of managing for just sequestration, as well as all the other things that we need to be managing for. So yeah, age is, I think, a good determinant of overall carbon stocks. Again, the other piece is most forests in the eastern US are not even aged. And so that's a little bit tricky in terms of managing that way. But larger trees usually tend to have more carbon, but there is this point where I think carbon, the rate of carbon sequestration increases at a decreasing rate when you get to a certain age, depending upon the sylvics of the species and the longevity of the species.
Great. I do want to do a quick time check and check in with Caitlin. I guess I've got maybe 4 or 5 more questions. Do we want to go through those, Caitlin, or any parting words for folks that got to jump off?
Yeah, so I'll do some quick parting words, and then if there's folks that want to stick around for those questions, I see no reason why not. Just a thank you for everyone for joining us. Eli did paste the link to request continuing ed credits. Remember, you need to complete that form if you want to receive credit for this webinar. It will open automatically when you close the window, and that's it. Just thanks for coming. You can go ahead, Matt.
Great. Well, not to go too far from the management topic, Grant, we have a couple of questions kind of focused on, management, and one that kind of captures it is, what about increasing the intensity of management? What kind of changes could we do to forest management that might increase sequestration rates?
Yeah, I think that's a good question, and one that I've been thinking a lot about, especially as it relates to what we were just talking about in terms of combating, or making forests more resilient to natural disturbances, maintaining forest as forest, and really avoiding emissions wherever possible. And I think, again, really this requires sort of a portfolio approach where, first of all, you identify your risks. So what forest types and in what areas are these areas maybe more at risk of insect or disease outbreak, or based on the composition of the forest or proximity to areas where we know that are high traffic areas in the case of invasive species, or in the case of fire, there are certainly fire prone species. Targeting those areas and management for those species one way versus how you might target other species less prone to catastrophic disturbance. I think that's the first piece. So sort of identifying, what are your goals and where are the opportunities? And so in the case where sequestration is really a priority, I think the key is maintaining high rates of sequestration. And I think there's a misconception out there, which is driven in part potentially by different markets and the metrics used by markets, but it's really that interaction with the atmosphere that's most important. How much carbon are you sequestering on an annual basis? We want to maintain high rates of sequestration in the same way that we want to maintain, high rates of growth overall if timber management is really our priority. So how do we manage that, that objective of maintaining and sequestering as much carbon as possible in those trees, with also the risks that come along with that? In some cases, the risk might be great enough that we aren't really managing to maintain super high rates of sequestration. Instead, what we want to do is just maintain high stocks in those areas. How do we maintain those high stocks and avoid things like if wildfire were to come through, spacing is such that those fires won't make it to the crown, for example. I know that that's less of a concern in places like Minnesota, but there are examples, certainly, particularly in the boundary waters in northern parts of sort of the subboreal region, where wildfire is an important consideration. And so for me, it's all about maintaining those high rates of sequestration. So what can we do from sort of a stand treatment and silvicultural perspective to maintain high rates of sequestration, whether that's on an individual basis or collectively? And then it's a portfolio. So there are going to be some stands that just aren't as productive as others. And so managing in a way where you can, manage for risk, but also, promote and make investments where that you've got the greatest opportunities for that positive interaction with the atmosphere and high rates of sequestration.
Great. And on the same topic of management, curious about the impact of management on soil carbon loss. I know this is something you've looked a lot at, Grant.
Yeah, well, that's a great question. And, I will say I'm not a soil scientist, number one, but we have spent a lot of time over the last number of years, in part because we know that soil carbon is the largest stock or sink of terrestrial carbon in the world, particularly as you move north latitudinally. The contribution of soils gets higher and higher, greater and greater. There's a lot we don't understand in terms of changes to that pool. I think the historically there's been this sort of weight of evidence to suggest that intensive management can lead to more rapid nutrient cycling due to soil warming, erosion, and just general disturbance. That's sort of what IPCC has said, and their suggestion is that we report soil carbon to a depth of 30 centimeters because it's really that area that's most prone to human activity. But I think there's also evidence and emerging evidence to support the fact that there can be positive gains as a result of management activities. I think I cited in one slide a paper that Luke Nave led at the University of Michigan, looking at reforestation on historically non-forested areas. And the contributions, we always think, and the focus of that reforestation study that was just published a couple months ago by our team was really focused on the live tree component. But what we didn't think about was the inputs of those live trees. Remember, early in stand development, forests are often carbon sources because of the respiration that's occurring through mortality and in the root systems. And so, thinking about the contributions of the inputs early in stand development, particularly in natural stands like aspen, where we know thinning is just rampant early in stand development. There's a lot of input to that soil carbon pool, and there's potential for those soil carbon stocks to actually increase over time. The same has been observed through actual empirical information in the case of afforestation activities and reforestation activities. And there is, I think, a real opportunity to maintain or enhance soil carbon stocks. Now, again, it's not sequestration because it's dead organic matter, but it's really through management. I think there are ways in which we can contribute inputs to that particular pool and at least maintain soil carbon. And in some cases, there's evidence where we're actually, particularly if you're going from sort of a cropland environment where you might be tilling the landscape to a forest land environment, there's certainly evidence where you're increasing soil carbon stocks. Now, forest remaining forest, where you're seeing intensive management, there's also been, I think, a weight of evidence to support the fact that there's been a loss of carbon. Now, the trick is, in these cases, measuring carbon is not easy. They're destructive samples. And so, how can you ensure going back there over time that, the spatial heterogeneity of these soils is such that really getting a statistical signal in these soils is challenging. The last thing I'll say about it is the Forest Service has about 8,000 soil plots, and we just started to get remeasurements for the first time. And we're starting to look at those and really ask the question, can we treat them as remeasurements at all based on the protocol? And so, that I think is an open question. There's a lot of uncertainty around soil change, but one thing's clear, soils represent an enormous sink of carbon in the US. The drivers of change are less clear. And so that's kind of how I'll close there.
Great. This is kind of a historical and a really historical question. I'll kind of merge these two questions into one, but your thoughts on why carbon has increased in Minnesota over the last 20 years. And then the second part of that is any idea what carbon looked like before European settlement a long time ago? Was it more or less or unknown? Your thoughts on that?
Great questions. Yeah, so and I think they're not mutually exclusive. They're related, right? So I think what we're seeing here is this sort of legacy of clearing post-European settlement and the rapid sort of recolonization, maybe by different species. So the aspen sort of occupies a lot of the landscape in the lake states that was once occupied by red and white pine and jack pine in some cases, as well as other species. We know that aspen is a fast-growing species. So I think compositionally things look very different pre-European settlement. What we're seeing over the last 20 years is really a reflection, I think, of the legacy of management, good management in some cases, and over time, because what we're seeing is sort of these different age classes, sort of, certain age classes are likely to sequester carbon at a more rapid rate than others. Early in stand development, once they've sort of the stands initiated, there's high rates of sequestration that occur to a certain point where that curve starts to asymptote or flatten out, and we're not seeing the same kinds of the same rate of sequestration. And so, maintaining those rates, an active state forestry program, there's a lot of public land in Minnesota, but the majority, I think, is still 60% is still private, and a lot of active management has led to a pretty strong sink strength relative to the size of the forest land base in Minnesota. And so I think, a state like Minnesota, there's huge opportunities. So there's a fair amount of understocked forest land. So I think there are definitely opportunities to increase the sequestration and sink strength in Minnesota's forests. But also, I think there's a lot to be proud of. It's a pretty strong sink. It's a sink that's growing. In a lot of states, We're not seeing that. In fact, we're seeing the opposite. And certainly what we're seeing in Minnesota is counter to what we're seeing nationally. So I know I've sort of, at the risk of being completely redundant, because I've said a lot about it already, disturbance patterns in the United States over the long haul, but really in the recent past where we've really been looking closely, we're seeing, basically US emissions have gone down. Economy-wide emissions have gone down since about 2005. That was sort of the peak, and things have gone down. There was a blip over the last couple of years where things went back up slightly, but overall, the trend over the last 15 years is that emissions have gone down. Over that same period, the contribution or of the forest land base to that reduction has been really stable. In other words, the sink strength is diminishing in the forest land base, and that's in part due to land change. So we're seeing a lot of abrupt loss of forests. So 100, 200 years, sometimes a millennia of carbon accumulated in an area that's lost pretty abruptly due to land change and expansion of urbanization and agriculture and other things. But the larger contributor there is disturbance. The largest disturbance in the United States remains harvesting. The key is there, a lot of the losses that we're seeing end up not being losses, but really a transfer into the harvested wood products pool. So I didn't talk a lot about it in this talk, but I think it is important that we follow the sort of, we need to track that carbon to the fullest extent we can until it returns back to the atmosphere, or in our case, as it leaves the categories that we contribute to. But what we found is that, really a lot of the management is you can manage for, intensive silviculture that might, that material might be used as a substitute for some more fossil fuel intensive fuel. It might be used as a replacement to fossil fuel intensive building products, or it might be used directly in building products, that have a really long half-life, building materials that might persist in a home for 100 or more years. So when you look at the whole picture and think about, from the stump to the mill to the end use, in some cases, not a lot of carbon is actually lost. And so you really need to take that into consideration too. While harvesting is a major disturbance in the US, the losses are made up for by the accumulation of carbon in those wood products over time, as well as in landfills. Yeah.
Great, thanks, Grant, and thanks to you for taking all these questions. I just have two more left, if we can get through those. One is about the Tongass National Forest, and your thoughts about kind of forest carbon there. And I know that's recently been in the news, but Tongass National Forest in Alaska. Your thoughts, if management were to happen there, could that increase the amount of carbon sequestered in that national forest?
Yeah, it's a good question. We have data in the Tongass. We've recently done a whole bunch of analysis comparing those coastal temperate rainforests to the interior forests of Alaska. And the interesting thing is, if you look at it, there's sort of this longitudinal gradient in carbon stocks and how they're distributed in these forests. In the Tongass, there's a lot of soil carbon, but these forests are decadent in a lot of cases because of a lack of management, or they're just natural forests. There's a lot of old growth forests in the Tongass. It's also very productive, so there's a lot of turnover and a tremendous amount of accumulation of dead organic matter in these systems. And so, I think in some cases it's hard to know exactly what they might look like moving forward. Although I talked to colleagues in the Pacific Northwest who are managing some of the temperate forests there, and they're seeing wildfire, what they're calling novel fires, on the sort of west side of the Cascades for the first time as a result of changing climate. And so, I do wonder how things might change in the Tongass as a result of management. Of course, again, this is an area where, there's a tremendous amount of carbon in above ground biomass right now. So the majority of the carbon is in the live and standing dead components of these forests in places like the coastal southeast and south central parts of Alaska. relative to the interior, where almost all of the carbon is in litter and soil. And so, I do worry that, just how you manage in particular is is a trick. Exactly. I can't even really begin to speculate how things might change, only to say that certainly management will have an impact immediately in terms of the overall carbon stocks there, because the above ground biomass is a major contributor right now to the overall carbon picture. And those forests are productive and they continue to sequester a lot of carbon. And so, my sort of assumption would be that through proper management, those forests would be maintained as forests. You'd have a loss of carbon, but that, the forest would come back. Now, the trick is, in some cases, the accumulation of dead organic matter in these sort of decadent ecosystems is such that, there have been a number of papers recently suggesting globally that managed ecosystems around the world, those forests are shorter, smaller diameter, and sequester less carbon than forests pre-European settlement. I think there's a substantial weight of evidence to support this, and I'm afraid that we would see the very same thing in a place like the Tongass, where this is really a novel ecosystem. Part of the reason that it that it's protected, that's in the national forest system and has historically had protections, is because of the unique nature of this ecosystem. And my expectation would be that if you manage it, you're managing it on a rotation that would be very different than the environment and then it's currently growing in. And you're not going to see these novel large trees and the amount of deadwood accumulating, because you're capturing a lot of that mortality through management. And you're likely going to see a real change in the structure and potentially even the composition of these forests, and also then the distribution of carbon. There's a lot in the live trees, but like I said, there's a lot in the dead organic matter, the duff later, the down dead material, etc. So certainly it would change. Now, in terms of the interaction with the atmosphere, how much would these new forests sequester relative to the current forests? It's hard to say. But what I will say is some of those species are long-lived and they continue to sequester at high rates, or have the potential to sequester at high rates. How that differs from a new stand, depending upon how they manage those, is, again, I'd be speculating, but certainly the structure of these forests would look very different.
Great. And then last question, we'll end on a positive note. The Trillion Trees Initiative, you mentioned that. The person is wondering how and when will it affect Minnesota public and private land reforestation? So maybe a little bit on what the Trillion Trees Initiative is, and then maybe impacts to Minnesota.
Yeah, sure. So, so the Trillion Trees, broadly in a nutshell, is a reforestation, restoration, and overall ecosystem management initiative established, I don't know, a few years ago, maybe. It's been around for a while. The concept has been around for a while, and I think there are actually, at one point in Forest Service, I was being told there are 3 different Trillion Trees initiatives. There's a Replanting Act, which I'm sure many of you have heard about, which they're all sort of related. The ambitions and intent are more or less the same, though, in terms of maintaining forest as forest, enhancing the capacity of forests to sequester carbon and provide a multitude of ecosystem services, not just carbon. And then in some cases, there are opportunities to restore native ecosystems through investments in planting, management, or in some cases, preservation. So that's in a nutshell how I understand the Trillion Trees Initiative. In January, President Trump acknowledged and announced at the World Economic Forum in Davos, Switzerland, that the United States would be signing on and participating in the Trillion Trees Initiative. Shortly after that announcement, our group was contacted by the White House to start compiling estimates of reforestation potential in the US. So I shared some of those results that have recently been published. That was really just a little snapshot of the work that we did as part of the questions stemming from the US's commitment. It's my understanding that the 1t.org regional chapter is being led by American Forests, a nonprofit in the DC area, and they're sort of building a lot of that out. We're working with them right now. I'm on a call just about every week. It used to be every single day about trillion trees, related to how this will be deployed, how the planting stock will be deployed, what land will be targeted, etc. It's not clear to me exactly how that will shake out, but what I can tell you from a Forest Service perspective is that we're working really hard to identify National Forest System lands that could benefit from some of the targeted activities that an initiative like Trillion Trees and other tree planting campaigns have set out, or with objectives around reforestation, recovery, and aiding recovery in areas where forest regrowth has been slower than expected. And so in a state like Minnesota, my expectation is that I can tell you, there are opportunities here. We've done the analysis in every single state. There's certainly understocked forest land in Minnesota that's productive, where there's evidence of trees in the past. And I want to make clear here, we didn't go into this analysis naively and suggest that all areas that are productive and where we know forest grew at one point are really prone or optimal for replanting and to make investments. There are a whole suite of things that need to be considered. And what is the current climate in these places? What is the current planting stock composition, as well as disturbance regimes, proximity to mills? All of those things need to be considered in terms of, as well as a whole variety of socioeconomic factors that we really didn't go into, but I fully acknowledge exist in terms of capacity. That's a big one. Planting capacity, nursery stock. What is the available nursery stock? That doesn't change overnight. And how do we grow that capacity and that infrastructure in order to meet the objectives or the goals set out by the federal government? Number one, I think the ambition is there. Certainly private enterprise, the federal government, and I think states are signing on in many cases, recognizing the opportunity and the contribution that forests and trees make as a nature-based solution, not just the carbon or climate mitigation, but the whole suite of other benefits that they provide. So yeah, what I would say is, if you're really interested in that, check out American Forests. They're sort of standing up some resources right now at sort of a regional scale. And those people, and if you want more information, you can contact me directly, and I can put you in touch with some of those folks that are working on it, or other people in Washington that are focused specifically on trillion trees, and how some of these investments and efforts will be deployed over the next year or so.
Great. Well, Grant, thank you so much for joining us this afternoon, and for taking all those were great questions. Thanks to everyone watching that submitted those. As you can tell, there's a lot to understand when it comes to carbon and its role in the greenhouse gas and our economy and all of that. So Grant, thanks again for joining us, and a great presentation on kind of the status of where we are. Caitlin, I'll turn it back over to you to close us out if you have anything else to add.
That's it. Just, thank you, Grant, for taking the extra time, and to everyone who asked all of those great questions and stuck around to hear the answers. We will, of course, send you the recording of the session, so anyone that had to leave early will be able to see those as well. And that's it. Look forward to seeing you all in the new year. Thank you, Grant, and thank you, everyone, for coming.
Thanks for the opportunity. Happy holidays.
You too.